In this problem, we're going to solve this question where we're given hydrocyanic acid and we're told it has a Ka of 6.2 times 10 to the negative 10th, and we are asked for what is the pH of a 0.2 molar solution of HCN. So to start this problem, we're going to start with a balanced chemical equation, and we're told that we're starting with HCN, which is a weak acid. One of the ways we know that is we are given this Ka, and recall that anytime we have a Ka, that's specific for a particular equilibrium. So we're going to write HCN aqueous plus water as a liquid in equilibrium with H3O plus aqueous plus Cn minus aqueous. And then we know Ka is equal to the concentration of our products, H3O plus times Cn minus, divided by the concentration of our reactants, HCN, leave water out because it's a pure liquid. So to solve this problem, this is a weak acid problem. It's an equilibrium problem. So we're going to go at it using an ice table, or rice table if you prefer. And remember, in our ice tables, we're going to start off and we're going to put in our initial concentrations. So the initial concentration of HCN is given as 0.20 molar. Since water is a pure liquid and does not show up in our equilibrium constant expression, we can ignore that and just leave that out. And at the start of the reaction, we don't have any hydronium and we don't have any cyanide ion. So for our change, so C is change, we know we're going to lose some HCN. Some of the HCN will react. We don't know how much yet, so we're just going to call it minus X. And then on the product side, we're going to form hydronium and cyanide. Since these are all in 1-to-1 ratio, we have plus X and plus X. And to come up with expressions for our equilibrium concentrations of each of these, we just add the I and the C together. So HCN ends up being 0.20 minus X, hydronium is X, and our cyanide is X. Now we're set up to substitute in to our Ka expression. So we can come down and write this. I'm going to say Ka, and remember the value of Ka we are given, 6.2 times 10 to the minus 10th is equal to now X times X over 0.20 minus X. And what we want to do now is recall the questions asking for the pH. So how are we going to go about getting the pH? And the key here is in our equilibrium, we hopefully recall that pH is equal to the negative log of the concentration of H3O plus. And so when we look at our ice table, we see that X we've defined to be the concentration of H3O plus. So if we can solve for X, we can plug it in to our pH equation as the concentration of hydronium and get the pH. So how do we solve this for X? There's a couple ways we can go about it. One way would be to multiply both sides by 0.02 minus X, and then we'd have a quadratic expression to solve. The other way is when we think about our equilibrium constant, we see it's 6.2 times 10 to the minus 10th. So this is a very small number, 10 to the minus 10. So remember, this is a ratio of products over reactants. So when we see such a small number, it means that almost everything is on the reactant side, and very little goes to products. That means this minus X is very, very small. And so one thing we can do now is we can assume that 0.20 is much bigger than X. And if we do that, our expression is going to simplify. So 6.2 times 10 to the minus 10th is now equal to X squared over 0.2. And now we can go ahead and solve for x. So let's see if we can't pull up our calculator. So we're going to multiply 0.2 to the other side. So 6.2 times 10 to the minus 10th times 0.2 equals 1.24 times 10 to the negative 10th. Now we have to take the square root of that. So I'm going to take the square root of our answer we just got, and we see that x is going to be 1.11 times 10 to the minus 5th. Now, we made an assumption, so we should check our assumption using the 5% rule. And in order to do that, all we're going to do is we assumed that 0.2 was much greater than x. Now that we know what x is, we're going to make a ratio. We're going to take that 1.11 times 10 to the negative 5th, divide it by 0.2 times 100. And as long as this ends up less than 5%, our assumption is valid. So I'm going to go ahead and do that in the calculator. So we're going to take our 1.11 times 10 to the negative 5th. We're going to divide that by 0.2. And then we're going to multiply by 100. And we see we get 0.006. So that's less than 5% by a lot. So our assumption is valid. So we now know what x is, right? So this x we've solved is the concentration of hydronium. So we can come over here to our pH expression, and we're now going to say pH is equal to the negative log of 1.11 times 10 to the negative 5th, and pH is going to be, and again we can pull up our calculator, so we have negative log of 1.11 second e to the negative 5th, close our parentheses, pH equals 4.95. So we can get rid of our calculator, 4.95, which hopefully should make sense. We started with a weak acid, HA, and our solution is indeed acidic. Thank you.